All right, we are going to continue optimization examples, and look at your guided notes. We're going to start with example 2. Now with this example, when you read the question, it says which points on the graph are closest to the point 0, 2. This means we want to minimize the distance between some point x comma y and 0, 2. So we want to minimize the distance, okay? So think, what formula or what equation do I want to use that deals with distance? Well, that's the distance formula. The distance formula as our primary equation. All right, so the distance formula, plugging in those points, x comma y, because that's an unknown point, and then 0 comma 2, you should end up with, oops, hold on, sorry, the square root of x to the 4th minus 3x squared plus 4. So let me just move that up so everybody can read that there. Okay. Okay, I'm struggling. Anyways, this is the distance that you get, and when we have that equation all simplified, the next step with optimization is to take the derivative of our primary equation. Before we take the derivative, we want to check that the equation is all in terms of the same variable. This is already all in terms of the same variable, so check that off. We want to then figure out what our realistic domain is. The domain here can be anything, because we're dealing with points, not some type of unit of measure. So the domain can be anything. So now let's take that first derivative. I'm going to just kind of work through this quickly, and if you're struggling with how I arrived at that derivative, you should try it on your own, obviously. Then we'll talk about it together. So the derivative of that distance formula, I'm just going to call it d prime because I had d equals. D prime equals 1/2, because I'm using chain rule, x to the 4th minus 3x squared plus 4 to the negative 1/2 multiplied by 4x cubed minus 6x. Again, I'm going to kind of skip some steps here, but just give you the final result of this. This derivative simplified and factored would be x times 2x squared minus 3 all over x to the 4th minus 3x squared plus 4 to the 1/2. So it's technically radical in the denominator. Now remember what our next step is. We want to set the derivative equal to 0 to find critical numbers. So setting this derivative equal to 0, looking at the numerator and how the numerator will equal 0, you get x equals 0 and x equals plus or minus the square root of 3 over 2. So those are some critical numbers. Remember, we also want to look at where the derivative does not exist. So we're going to look at our denominator now. And where the denominator equals 0 is at plus or minus 2. So next we want to make our sign chart using these points as our breakup in the intervals. So I'm going to be evaluating my sign chart from negative infinity to negative 2, and then negative 2 to negative rad 3 over 2, and then negative rad 3 over 2 to 0. I might run out of room. 0 to radical 3 over 2. Radical 3 over 2, this is just a long one, sorry, to 2, and finally 2 to infinity. Wow, took up the whole space. So remember what we do with our sign chart. We pick test points. So pick any test points that you want that work in those intervals. Again, I'm going to work through this a little bit quickly, so I want you trying it on your own as I'm going through it. when you do a test point in the first interval, you end up with a positive result with the derivative, okay? With the second interval, you end up with a negative result. With the third, it's a positive result. With the fourth interval, it's negative, then positive, then negative. So remember what it is that we're looking for. We're trying to minimize something. So I don't care about the maximum values here. I want to just know where the minimums are. So I will have a minimum anywhere we change from decreasing to increasing. So from decreasing to increasing, I just figured out where my intervals, where my critical numbers are going to be minimums. So that happens at negative radical 3 over 2 and at positive radical 3 over 2. We have two minimums. So my minimum values were at the points negative radical 3 over 2 and positive radical 3 over 2. And don't forget you have to plug those numbers back into the original function or equation. So we're plugging this back into that original distance equation. And then we get an output of 5 over 2 for both of the y values. Okay, so how does this answer our question? The question was, which points are closest to the point 0, 2? So these are the points closest to 0, 2 on that graph. And if you wanted to verify this, you can look at your graphing calculator and determine that. All right, let's move on to another example. All right, in example 3, if you read the problem, it says a rectangular page is to contain 24 square inches of print. The margins at the top and bottom are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? When it's saying least amount of paper, it's saying that we want to minimize the piece of paper. So the first thing I would do here is draw a picture. I would draw a piece of paper of some sort. So in doing so, it's not going to be perfect, but I have a rectangular piece of paper, and we know the margins on the left and right. So we can label those as so. Like I said, don't judge my picture. So on the left and right, we know we have 1 inch margins. And on the top and bottom, we know we have 1.5 inch margins. And we can call the lengths of the inner part of the paper, we can call the lengths of those x and y. We don't know what they are, but we can find them. So let's just call them x and y. So I'm going to label this inner part, x, and then the top and bottom dimensions of that inner part would be y. Alright, so we want to minimize this, so we want to figure out an equation, right, our primary equation, which would be area. So you want to think, what would the area be using this picture? How would we write the area? Well, the left and right are both 1 inch margins. So if I take that y value, or the length here that is y, and I add the left and right to it, I get y plus 2. If I take the x value and I add the top and bottom to it, I get x plus 3. So the area overall, being base times height, is just x plus 3, because it's the 1.5 and the 1.5, times y plus 2. The 1 plus the 1 plus the y. Alright, so simplifying all of this, we have the area equals x plus 3 times, what I'm about to do is change that variable y in terms of x. Well, how can I do that? Because remember, the next step is to put everything in terms of one variable. How could I possibly just rewrite that y in terms of just an x? I want it to just be something with an x. Well, we had an important piece of information in the problem. It told us that the rectangular page contains 24 square inches of print. So I know that that little inner part, the X by the Y, that has an area of 24. So off to the side here, I'm going to go ahead and write that for you. We know that 24 equals the area of that inner part, X times Y. Dividing both sides simply by X gets Y alone. So I have Y equals 24 over X. So that's what I'm going to do to replace my Y. Okay, so now that that's done, you want to distribute everything, clean it up a little bit, and you'll end up with 2x plus 72 over x plus 30. The next step to this would be to take the derivative. Okay, so this one's a bit nicer. When we take the derivative of this, quite simply, a prime is equal to 2 minus 72 over x squared. So again, remember this procedure when we're trying to maximize or minimize something. We want to just set the derivative equal to 0 or find out where the derivative does not exist. So setting this derivative equal to 0 and figuring out maybe where the denominator will be undefined in any part of the function. So this function, setting it equal to 0, again, guys, I'm kind of skipping the algebra here, but you should get x squared equals 36. So x equals plus or minus 6. And then where the denominator does not exist, or is undefined, so where the derivative does not exist is at 0. So these 3 points here are our critical points. But remember what we're working with. We're working with an actual piece of paper that has dimensions. So -6 is not a possible answer. Okay, so we eliminate the -6 and we're only looking at 0 and 6 for our intervals. So those are going to be our critical numbers that we use. All right, so setting up our sign chart from 0 to 6, right? And then technically 6 to infinity. Think for a minute why I wouldn't do negative infinity to -6 and -6 to 0. We can't have negative dimensions. So what I'm going to look at here with my test points, I'm going to plug back into the derivative and figure out where it is increasing and decreasing. So it is negative on this interval, positive on this interval, which indicates I have a minimum at 6, okay? So x equals 6 is my minimum value, which answers our question. So we know that the 6, which represented x, is going to be the dimension for the minimal amount of paper, to minimize the piece of paper. So if you take that 6 and plug it back in to your area equation, 24, which was the area, equals x. Now we can replace that with our 6 times y would leave us with y equaling 4. So then plugging that back into the original image, remember that original picture, and adding those margins on the side, we have a piece of paper with dimensions 6 by 9. All right, and we'll work through the other examples together in class. Thanks.